think I gave you anything to do in here, but again, my take on Wronskians is kind of outdated. If you really do have something linear, you're not going to do this. If you're like me, I'm just going to go calculator, ODE, solve it for me, and find the first Google site that'll do it for you. Nobody's calculating the Wronskian anymore. So this is a little bit outdated, but it develops character. So let's cover it. So in this case, this is Abels' theorem. Abel is a famous mathematician that did a lot of things in differential equations. If you have two solutions to the second order equations, then the Wronskian of the two solutions, which is they're calling the determinant, is equal to the original matrix with y1 and y2 with t0 plugged in times e to the minus, and I think that should be determinant. I forgot my determinants here. Should be these. Otherwise, it doesn't make sense. Times e to the minus p of x t dx. What this does is it gives you a way to calculate something that you don't know the solution to. So it'll be useful to you if you can't grind out the solutions. Okay, it's still there. So why this is useful is you can rewrite this as just a constant, a determinant is a constant. Absorb all the constants that are around it, and you really get this guy over here. I'm going to show you how to actually apply it, what you use it for. So here's a second order differential equation. It's non-autonomous. Something's non-autonomous if it has t's in it. It doesn't just have the y's and y double primes and so forth. You rewrite that equation so that the coefficient of y double prime is 1. The book is actually really good. This is like a recipe book. It's telling you recipes of how to do things. So it always tells you, hey, the coefficient of the leading derivative, the highest order derivative, has to be 1. So you have to divide through. I'm a mathematician, so as soon as I divide through by t, I'm also putting a little addendum in the margin that says t is not 0. So off it goes. And then you use the Wronskian formula from Abels' theorem, which is this guy here, and I get this thing. And I'm just going to ignore constants of integration because they can all be stuck into that c. When you integrate with definite integrals, you're going to have constants of integration. So they're just going to pop into the c. And so I get ct squared. What it's used for is I can look at that ct squared and ask myself if that's, under what conditions would that be 0? You can look at it and tell me what conditions would that be 0. T is 0, I assume t is not 0 to begin with, so t is 0 is bad. Anything else that could cause this Wronskian determinant to be 0? If c is 0. So if you have some kind of initial condition or something that drives that c to be 0, you're not going to be guaranteed independent solutions. I'll wait till you catch up. Good? So what can you conclude? That the two solutions to the equations are linearly independent if ct squared is not equal to 0. And just like you just said, as long as c is not 0 and t is not 0. The notes are always popped up on the calendar invite, so you have this. We'll tell you in advance if there's going to be something on the midterm that has this, because this is like, I have to wrangle with Dr. Groves and see what she thinks. So what that means is if your initial condition starts at 0, all bets are off. I made a lot of assumptions about T not being 0. So you might not have uniqueness of solutions. You might have a hot mess. You've already seen that.